Hey guys, welcome back. This is Mr. Hoying. I am here to finish off the last of the Chapter 3 notes. Today we are going to talk about the Molar roadmap and how to do more complicated conversion problems, 2 or even 3-step conversion problems. So the Molar roadmap is basically a visual device that kind of collects all the different conversion factors that we learned about into one spot. And you can see here that this is a picture of it. Basically, the Molar roadmap provides a way to get from any of these conversions, mass, representative particles, volume, to any of the other ones. And everything goes through moles. And that's kind of the important thing to see here, is that all of these go through moles. Moles are very, very important in chemistry because moles measure amount. It's our SI unit for amount. And chemistry happens in units of amount. That's just the way it works. We're going to, as we get into the chemical reaction part of our year, that's pretty much what we're going to be looking at, is the amount, the number of molecules of substance A are reacting with the number of atoms of substance B. We're not talking about grams or volume, we're talking amount. So it's really important to be able to get into amount, out of amount, because typically when we express how much of something we have, we don't want to use amount. We want to express it with volume or mass or something like that other people will understand. So it's good to be able to move between all these different units. And again, we can see that there are conversion factors in between. To get from mass to mole, it's molar mass, which we calculate from the periodic table. To get from mole to volume of gas at STP, it's molar volume, 22.4. And to get from mole to representative particle, which is an atom or a molecule or a formula unit or something like that, we use Avogadro's number, 6.02 times 10 to the 23rd. So let's go ahead and do some sample problems. How many molecules are in 45.6 grams of water? Well, I'm going to start off writing down my starting value here, and I think I need to get a pointer, a pen here. We have 45.6 grams of water, and I want to convert that from grams, let me just go back here, to molecules. Molecules is a representative particle, so I'm starting off here with grams, and I want to get over to here with representative particles. So how do I do that? Well, mass to moles, I'm going to use molar mass. So I use molar mass of water first, and then moles to representative particles, I'm going to use Avogadro's number. So it tells me as I go along the map what I'm converting to and what I need to use to make my conversion. I'm going to use molar mass first to get to moles, and then I'm going to use Avogadro's number second to get to molecules. And molecules is the representative particle for water because water is a molecular compound. It is not an element. If it were an element, we would have to use atoms. So 45.6 grams of water. Water is 18.0 grams per 1 mole. I've already calculated the molar mass. And then to get to molecules, it's 6.022 grams per 6.022. Erase. Times 10 to the 23rd molecules per 1 mole. So molar mass, Avogadro's number, arranging so that units cancel out just the way I want. And I'm left with molecules, which is the unit I want. So I'm going to go ahead and pause to calculate. And I get 1.52557 times 10 to the 24th. I'm going to round that off to 3 sig figs and get 1.53 times 10 to the 24th molecules. And there we are. Let's try another one. How many liters of chlorine gas would be in 4.07 times 10 to the 25th molecules of the gas? And this is, even though it doesn't say, we're going to go ahead and treat this as though it were at STP. So liters of chlorine gas from molecules, let's go back to the roadmap. Liters of gas, molecules of gas down here, so representative particles, we want to get to liters. Up here, we're going to go this way, okay, through moles using Avogadro's number, and then molar volume. So Avogadro's number followed by molar volume. 4.07 times 10. You know what? I'm going to pause and fill in. So we went ahead and calculated everything out using first Avogadro's number, like we said, and then molar volume. Arranging everything, flipping Avogadro's number so that molecules would cancel, and then writing in molar volume, I guess right side up. So we'd have liters on top and moles would cancel on the bottom, and we end up with an answer of 1,510 liters. So again, you know, linking these conversion factors together, not really that difficult. It's just a matter of saying, okay, which route am I taking on the molar roadmap? How many grams of methane could be found in 32.5 liters of the gas? So we've got 32.5 liters. We want to get to grams, liters, grams. We're going to use molar volume first, molar mass second. Molar volume first, molar mass second. So 32.5 liters. And it's 22.4 liters per 1 mole. And then the molar mass of CH4 methane, carbon is 12, and we have 4 hydrogens at 1.0 apiece. So we're going to end up with 16.0 grams per 1 mole. And then we calculate, and we get 32.5 times 16 divided by 22.4, and we get 23.2 3 sig figs grams of CH4. Again, the reason we have 3 sig figs, this is all multiplication and division. 3 sig figs, 3 sig figs, 3 sig figs. Yeah. All right, last one. This is a little bit more challenging of one. If lead has a density of 11.3 grams per milliliter, how many atoms of lead will be needed to make a cube that is a length of 4 inches? Lead is indeed an element, so atom would be the appropriate representative particle. So let's go ahead and talk about what would be a good starting spot here. They're giving us density, 11.3 grams per milliliter, so we know that. And then they're giving us the fact that it's a cube that has a length of 4 inches. What is a good starting spot here? Well, density is not the best starting spot because density is a derived unit. It's got grams per milliliters. It's something per something else. It's going to make a good conversion factor. And it's going to give us a bridge between mass and volume if we need it, which I think we will because lead is a solid. What we're going to actually use as our starting point is the volume of the cube. And the volume is really simple to find. We have a three-dimensional object. We know the length of one of the sides. Volume would be handy because if we know volume, we can use density to get over to mass. So I'm going to start with 4 times 4 times 4, or 64.0 inches cubed. All right? And I want to get from inches cubed to milliliters, so I'm going to do that the old-fashioned way. For every 1 inch, there are 2.54 centimeters. And if I cube inches, I also have to cube the 2.54. That's going to give me centimeters cubed. And there's 1 milliliter for every centimeter cubed. So now I'm in milliliters, so I can use my density, 11.3 grams per milliliter. 11.3 grams per 1 milliliter. And now I'm in grams. Once I'm in grams, I'm home free because grams gets me on the molar roadmap. I can go click, 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 all the way back here. I should have put a second one in. I should have bookended, really. Not good planning. Grams, and I want to get to atoms, so that's the route I'm going to take. Grams, I'm going to use molar mass to get to moles, and then I'm going to use Avogadro's number to get to representative particles. So let's go back to our problem here. the molar mass of lead, and lead's an element, so I'm just going to look on the periodic table, and lead is going to be 207.2. 207.2 grams per mole. So 207.2 grams per 1 mole. And then finally, to get to atoms, I'm going to use Avogadro's number, 6.02 times 10 to the 23rd atoms. And again, the reason that the representative particle is atoms is because lead is an element. If it were a compound, we would use molecule, or if it were an ionic compound, we'd use formula unit. Boop. Inches cubed is gone. Centimeters cubed is gone. Milliliters are gone. Grams are gone. Moles are gone. We're ready to calculate. We're in atoms. We're good to go. Look at this. Dimensional analysis. Back stronger than ever. I love it. I'm going to pause while I calculate, and then I'll be right back. I'm back. The answer, as you know, the calculator says it, is going to be 3.443232, blah, blah, blah. 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. Everything else has infinite significance, so 3.44 times 10 to the 25th atoms. And that is your final answer. So again, I think that is pretty much it for this chapter. We'll work on these in class, do some practice with them in class, and I think we're looking at a test sometime late next week. So if you're watching this on Thursday, the 26th, a week from today will be October something else. 2nd, 3rd, but next Thursday is probably when we're going to have the test. So plan for that. We'll see you in class. Have a great afternoon. Have a good homecoming if I don't see you, which I'm sure I will because it's only Thursday, and I'll see you tomorrow hopefully. We'll see you then. Bye.